Okay. So let me share my screen. My screen is visible to all of you. Okay. All right. So welcome to the second live session. In the previous live session, we have talked about our course up to week number 5. And now let me actually, what's the agenda here in this live session? I want to talk about firstly, very briefly, I will talk about what we have done in week 6, 7, and week number 8. And also after that, I will briefly talk about, in fact, you should also know how relevant this course is. And finally, I will give you some name of some textbooks, which actually I told you in the last class as well, in the last session also. But once again, I'm going to remind you the textbooks which you can follow for this particular course. And as I said in the last session as well, that some part of this course is based on this textbook. So I'll talk that about at the end. So in the week number 6, we basically started discussing quantum optics in the completely quantum regime. In the earlier weeks, if you remember, we talked about semi-classical quantum optics, where we have considered light as a classical object and matter as a quantum object. But now what we have done week number 6 onwards, that light itself is a quantum mechanical object, and that means we have discussed about the quantization of light. And when we have discussed quantization of light, ultimately we follow this uh, procedure of canonical quantization, and this I have discussed in great lengths there in my classes. But let me again talk about, briefly remind you about what this canonical quantization procedure is. Generally, what happens that users consider any system, classical system for that matter, as an example, the harmonic oscillator. And this harmonic oscillator, you see, you can write down the Hamiltonian of this harmonic oscillator in terms of the momentum and the coordinate. And then you find out what are the canonically conjugate variables. Obviously, here the momentum and the coordinate are the canonically conjugate variables, and that you ascertain by checking whether these Hamilton's canonical equation of motions are satisfied, right? And then, of course, these two variables, canonically conjugate variables, should also obey this Poisson bracket relation. And once that is done, then the quantization from that part onwards is very easy. You replace this canonically conjugate variable, say here Q, by Q cap and P by P cap, right? And then this Poisson bracket is now getting replaced by this commutation relation, QP is equal to I H bar, and then you write down the Hamiltonian in this operator form, and your quantization is done. So this is a simple procedure to do quantization. So the same approach we have done with the electromagnetic field, for example, the light, which is an electromagnetic field. There we actually, the procedure that we have adopted, we have considered starting from this classical electric field expression, and this is E0, which is the complex, the amplitude of the electric field. And it's because it's a complex amplitude, it has a real part and an imaginary part. And we saw that this real and imaginary part of the electric field amplitude behaves like canonically conjugate variable, and this canonical conjugate variable ultimately obey the Hamilton's canonical equation of motion, and thereby ultimately we are able to do the quantization. And we have done the quantization for two waves. One is the propagating electromagnetic wave. All these things I don't want to repeat once again because I have done all these things. These things I have discussed in great detail in my classes, lecture classes. The idea was that to get the Hamiltonian, and we have considered an electromagnetic field in free space, and the Hamiltonian can be written in this form, right? And then ultimately we are able to write it in the this form where Q and P are exactly not position and momentum, but they are canonical conjugate variable associated with the electromagnetic field. And then we have adopted this second quantization procedure, means we can write Q and P in terms of this annihilation and creation operator, and thereby we can write down the Hamiltonian in the usual form. So the main result that we saw in week 6 in particular is that light, when it get quantized, it behaves like a harmonic oscillator. Each mode of the electromagnetic field behaves like a harmonic oscillator. So that is the core idea, that core lesson that we have learned. And we can therefore now, because this electric field, magnetic field, all these are now quantum mechanical quantities, so they can be represented by operator. And from basic quantum mechanics, and this I again and again repeatedly told you throughout the course, that any physically observable quantity in classical mechanics is going to be represented by operator in quantum mechanics. Okay, so right. And also we have done the quantization of standing wave as well, quantization of propagating wave and quantization of standing wave. Both of them actually shows that each mode of the electromagnetic field behaves like a harmonic oscillator. However, the concept of photon is slightly different in the case of propagating wave and in the case of the standing wave, that we have learned that in the case of the propagating wave, you see, the photon has a definite energy and a definite momentum. This we discussed. And in the case of the standing wave, the photon has a definite energy, but it does not have a definite momentum, because if you make a measurement of the photon momentum in the case of the standing wave, then either it has a momentum h bar k, or its momentum is zero, because standing wave is formed by superposition of two forward propagating and one backward propagating wave. That's the reason the momentum is basically not defined, but the energy is defined. So that's the basic difference in terms of photon for the propagating wave and the standing wave. Right. So this is what we did in the week 6. One of the item that we touched upon is the quantization of light that we discussed. Then we went on to discuss photon statistics, and because how to distinguish the for this electromagnetic radiation behavior specifically from the classical one, then one of the best thing to do is to study the statistics of the photon. Okay, and this we have done in week 6 itself, and there we saw that when there are three kinds of statistics a photon may exhibit. One is the so-called the Poissonian statistics, where we saw that the standard deviation, or simply if I take the variance, for example, this delta n is the standard deviation in the photon number, but delta n square, if you take, that's the variance. So if the variance is equal to the average number of photon, that means that refers to the so-called Poissonian statistics. But if this variance is less than this average number of photon, then that's called the sub-Poissonian statistics. And if it is greater than the average number of photon, if the variance is greater than average number of, that's the super Poissonian statistics. And sub-Poissonian statistics has no classical counterpart, by the way. And this also we touched upon in week number 6. Then we went on to discuss the so-called second order correlation function, which basically tells us about the probability of detecting two photons at the same time on a detector. Okay, and basically, if I say Z2 of 0, that means detect what is the probability. It is not exactly probability, but it gives you an idea about the probability of detecting two photons. If I take R1 is equal to R2 and T1 T2, if I set it to be at 0, that means at the same time, what is the probability that I can detect a photon at the same location of the detector? That gives you the idea about the second order correlation function. And we also learn how to calculate this second order correlation function. Okay, this is what we did, right? And that this is the general expression that we got. And thereby we can check, for example, if we have photon number state, then this is the expression we got. And on the other hand, for thermal light and the coherent light, these are the second order correlation function that we obtained. These things we discussed in week number 6. Then we went on to discuss the coherent states of light, which is basically it's a state which is which you can write as a superposition of number state. In fact, what turns out that coherent state is basic kind of eigenstate of the annihilation operator, right? This we discussed. And uh, more rigorously speaking, what turns out that coherent state is nothing but the displaced ground state. And we introduce the concept of this displacement operator. What happens is that by displacing the ground state, by applying by this displacement operator on the ground state, you can easily get what is the so-called um, coherent state. And in the case of the coherent state, we also discussed about the standard deviation of this quadrature operator X and the quadrature operator of Y, and the product of their standard deviation is equal to 1 by 4 for the coherent state. And these are kind of minimum uncertainty state. Whenever this two product is equal to 1 by 4, and that is exactly the case even for the case of squeeze states, which also we discussed in our discussion. And from this diagram, you see this coherent state is indeed, it's basically nothing but displaced ground state. And as the ground state is represented by a circle like this in this XY plane, uh, and now it is shifted by some amount of mod alpha. And this quadrature operator are defined in terms of the annihilation and creation operator in this form: x is equal to a plus a dagger by 2, y is equal to a minus a dagger by 2y. We also we did actually a couple of problems also exploiting these properties of this displacement operator, and these properties are important, and we actually proved some of the properties in our lecture class itself, and some actually in the problem solving session. We went on to discuss the squeeze state. The difference is that now here what happens that the unlike the coherent state where the quadrature, the standard deviation in x quadrature and y quadrature are exactly equal, but in the case of the squeeze state, one of the quadrature is getting squeezed um, at the expense of increasing the quadrature of the another one, right? That's why it is called squeeze state. But overall, it is done in such a way that the product of their variance standard deviation remains intact, that is equal to 1 by 4. Okay. Then squeezing operator, just like displacement operator, we can have a squeezing operator, and we can get the so-called squeeze vacuum state by applying this squeezing operator, and all these things we discuss in great lengths in our lecture classes already. And we talked about this squeezing Hamiltonian and properties of the squeezing operator also we discussed. We have done a lot of problems based on this squeezing operator. And I hope you have already gone through the problem solving sessions. Then week 7 and week 8 is particularly important, as you will see, because here we are applying quantum optics to certain areas which are obviously uh, is at the center of current research. One is the superconducting quantum circuit. That is what we have covered in week number 7. And in this context, we have discussed about this. First, we have started by discussing general idea of superconductor I gave you. How it is different from a so-called metal is that there is a kind of a band gap is there, and this band gap arises because of the fact that in superconductor the charge carriers are Cooper pairs, and these Cooper pairs are bounded. They are basically electrons bounded by this phonon interaction. And if you really want to break these two electrons, you have to apply energy. And because you have to apply energy to break this Cooper pair, and that gives rise to the so-called this band gap. And one of the theory that discusses superconducting phenomena, particularly at low temperature, is the so-called BCS theory, which we have discussed in some qualitative sense we discussed, but one of the important result was that the connection of this band gap at the absolute zero temperature and the critical temperature, and this was one of the most important result of this BCS theory, and this we discussed. And another important thing is that the magnetic flux in a superconductor is quantized, and you see this magnetic flux is integral multiple of the so-called flux quantum, and this is an enormously important result. Um, and then we discussed about Cooper pair box. Cooper pair box is simply two superconductors. If you place them adjacent to each other, then the Cooper pair may tunnel from one to the another one. And of course, if you have to choose the parameters in such a way, and already if you have done this week's lectures, if you have gone through that, then you know that here the charging energy part is dominant over that of the Josephson energy part, then it is basically then it is a Cooper pair box. Otherwise, it would become a transmon. And this I have discussed in great details in the lecture classes. And this is the whenever there is coupling is there, we saw that this avoided crossing phenomena is shown here, and you can now choose the parameters such that this Cooper pair box can behave like a two-level atom. For example, if we set Ng is equal to 1/2 or Ng is equal to -half, or say 3/2 and so on, then this Cooper pair box behave like a two-level atom, or it can behave like a qubit. And this parameter Ng is basically related to the external voltage, gate voltage that is applied to the system, right? We have worked out this Hamiltonian, considering this as a two-level atom to our qubit. This we discuss in great length. And also what we learned is that this Cooper pair box, when it is behaving like a two-level atom, the energy difference between these two energies, two levels, is equivalent to microwave frequency. So therefore, if you really want to study interaction of this two-level atom, that means this Cooper pair box with a electromagnetic radiation, that electromagnetic radiation cannot be a light wave, it has to be a microwave, right? And this we learned. That's the and another thing that you also have to maintain the Cooper pair box or the Josephson junction at a very low temperature, so that thermal fluctuation is not going to you know is not going to otherwise what is going to happen that you will not be able to discrete nature of the energy levels are, if you really want to maintain that, if you really want to um, study that, then the difference between the energy levels has to be greater than that of the energy corresponding to the thermal energy, right? And in fact, you see here, for example, if the thermal energy, if you keep operating temperature is around 20 millikelvin, then the thermal energy is 2 micro electron volt, and that's why this energy difference between these two energies has to be greater than this 2 micro electron volt, and indeed this is around 20 micro electron volt, and which is greater than the thermal energy, and then safely this system can behave like a two-level atom. This we discussed. And this basically leads us to this particular structure, this architecture, where we are having this resonator. This resonator is formed by breaking this transmission line at 2 points. I discussed this thing in the classes, lecture classes. And this microwave then can interact with a Cooper pair box. And this architecture is particularly important because this is, I think, the architecture based on which this Google quantum computer is inspired. This is a famous paper in 2004. And by going through this course, by this week 7 lecture, I hope you are at least able to figure out, you have understood how all these things are working. And we also learned that this about the, I have also discussed about the concept of this transmission line, and we can model it by considering at a series of, this kind of a LNC. Okay, and we have also discussed about the quantization of the LC oscillator, and here this magnetic flux is behaving like a coordinate and the charge is acting like a momentum, and thereby we can, these are your canonically conjugate variable, and then you can quantize this LC oscillator. In fact, I will discuss this point. Quantization of electrical circuit is the topic on which this year's physics Nobel Prize was given, right? And maybe most of you are aware of it. And that's the reason why this course is so important. Particularly week 7 is what we are discussing is based, if you can understand that, you will be able to understand the work that this 3 Nobel laureate has done and for which they have been awarded the physics Nobel Prize this year. That's why this particularly this week 7 is very important and very useful. Okay, then we have discussed quantization of LC oscillator, and after that we can of course write this magnetic flux operator and the charge operator. We can write it in terms of the annihilation and the creation operator, and thereby you can again write it in the usual harmonic oscillator Hamiltonian. And we discussed about how this two-level atom is interacting with the microwave radiation, and this is the interaction part of the Hamiltonian. And we can consider this Cooper pair box as a two-level atom like this, with having energy difference of this much h cross omega atom. And right, this eventually this led us to the this James Cummings model, which we also discussed in great length. Um, we discussed about the transmon qubit. In the case of the transmon qubit, the magnetic flux part become more dominant over the charge part. All this, and we see the transmon Hamiltonian is in fact, it's just a slight deviation from the usual harmonic oscillator Hamiltonian. If you can neglect this enharmonic oscillator term, then you see this Hamiltonian is quadratic in the number operator and quadratic in the phase superconducting phase operator. Therefore, it's a perfect harmonic oscillator. But then because of this enharmonicity, then it's not an exactly an harmonic oscillator. But this enharmonicity is needed. Because of this enharmonicity only, you can consider, you can tune the atom in such a way that it can behave like a two-level atom or a qubit. Okay, so when it behaves like a qubit, by choosing the appropriate parameter, then we can just discuss it just like a two-level atom. Then we went on to discuss in week number 8, we explored one extremely important area nowadays, what is this called cavity quantum optomechanics. Here, it's very, I think I have discussed it in great detail there in the live classes. You see, we have now, it's kind of a Fabry-Pérot cavity. In a usual Fabry-Pérot cavity, you have two mirrors separated by some distance. But here, in cavity quantum optomechanics, we allow one of the mirror to slightly move. So we have a movable mirror, and laser light is getting incident on it. And if resonance condition is satisfied, then the laser photon will be able to enter into the cavity, and then it is going to hit this mirror and thereby applying some kind of a radiation pressure on it, and then it can displace it. So basically that's the idea here. And this displacement can be caught by a radiation that is ultimately getting transmitted from this mirror, and this is going to give you an idea how much displacement this mirror has suffered and so on, and thereby you can derive a lot of important physical quantities, and you can get to know a lot about the system. So the most important concept here is the radiation pressure force, and this I have discussed there. In fact, what happens is that whenever this photon is, the idea is very simple. When a photon is hitting a mirror, this mirror, there is a change of momentum is there, and because of this momentum, this a force is applied on the mirror, and this is your 2p by c, where p is the pressure, radiation pressure. This anyway I have discussed there in the class. And most intriguing and quite surprising is that there are varieties of optomechanical system of different shape and figures, as you can see, and also having their mass range can be very different from gram to femtogram. Femtogram means 10 to the power minus 15 gram. Not only that, even from femtogram to zeptogram, I think around 10 to the power minus 21 gram, so small. All these varieties of structure can be explained. All these things can be modeled by the simple model, where you have one fixed mirror and one movable mirror connected to, it's a movable mirror, it's an oscillator, an oscillating mirror. And you can do lots of analysis, whatever be the shape and structure of this system may be, you can model it. So in this context, we have worked out this optomechanical Hamiltonian, and the basic idea was that when this photon is hitting one of these movable mirror, you see, usually if the mirror is fixed and x is equal to 0 here, because it is fixed, it cannot move, then this is the resonance frequency n pi c by l. But because there is a very small displacement is there, you can write in this expression. So therefore what you see, that this resonance frequency is now dependent on the displacement, and it's given by this, and this gives you this expression for this Hamiltonian here, right? And we discussed this particular Hamiltonian, where this part represents the energy of the photon inside the cavity, and this second term represents the energy of the phonon. I'm not writing plus half term because that's just a constant term. So you are having two harmonic oscillator. One is this because of the photon, which is behaving like when it is quantized, it behaves like a harmonic oscillator. Then you have this phonon, right? That's because of this mechanical oscillator. And then this is the interaction term between the photon and the phonon. And apart from that, you have to also consider that you are driving the whole system by applying a laser. And this is the drive term. And you can get rid of this time dependency by going over to a appropriate frame of reference by making unitary transformation, and all these things we discussed. And finally, when you have done the rotating wave approximation and you go over to a particular appropriate frame of reference, this is the Hamiltonian you can write, where delta is the detuning parameter. Now here you are able to get rid of this explicit time dependency, or equivalently this harmonic oscillator, this mechanical oscillator you can write in terms of p square by 2m plus half m omega m square q square. Rather than writing it as s cross omega m b dagger b, you can write it in this form also. And many times this way of writing the Hamiltonian is quite useful. And we discuss all these things in detail. And then we went on to discuss quantum Langevin equation, right? And this basically comes from just by applying the Heisenberg equation of motion, you can get this Langevin equation. Only thing is that now you are incorporating the various decay terms. For example, the this part here, this decay of this gamma is there, and Langevin noise that is entering into the system is also taken into account. And in the case of the photon, then there may be vacuum fluctuation is there that you have taken into account in this equation. All right, so then we also discuss about the linearized optomechanical Hamiltonian without taking into account all other quantum noise. Then this is the linearized optomechanical Hamiltonian we obtain, and we can rewrite it in this more, convenient form. We can write the Hamilton in this form. So overall, the meaning of this Hamiltonian means that you are having two harmonic oscillator. One is due to the photon and one is due to the phonon, and they are interacting with each other. And by this diagram, you see you see you have two oscillator, photon oscillator and phonon oscillator, and they are getting coupled to each other. The phonon oscillator is connected to environment at a temperature T. Photon, as we have discussed, it always at a zero temperature. Even at room temperature, you can consider it to be zero because it's behaved like a quantum mechanical object because of its high frequency. You can consider it to be as if it is at zero temperature. And now because this phonon oscillator is connected to the photon oscillator, which is basically a cold object, and phonon is a hot object. When two hot and one cold object are in touch with each other, then hotter object eventually become cooler, and that's the way that this phonon oscillator, which is a hot object, it's basically get cooled. And we have discussed about optomechanical cooling more technical terms in detail in the lecture classes. And we have, apart from that, we have discussed about squeezing, and I have given you about some idea about the quantum entanglement in optomechanical systems as well. Now, finally, just to let you just know once again that this year's Nobel Prize was on for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. By electrical circuit, exactly this is the one they have basically meant, right? And basically their work, this Devoret and Clark and Martini's work greatly influenced lots of stuff later on. And this was one of the work where I think this guy, uh, Devoret, is also one of the author, if I remember correctly, of this paper that published in Physical Review A in 2004, who is ultimately inspired Google to make their quantum computer. We discussed all these architecture and all these things are there. If you have gone through this, maybe you are at the moment, you may be on it, or you have just completed lecture 7. I'm not very sure. So if you have not done that, then or if you are going currently in week 7, then you must be encountering these lectures already. Okay, so I think I have already discussed all these things in my lecture classes, that these are the two main results. One is that this is what was discovered by Brian Josephson. When you have this Josephson uh, junction where you are having two superconductors separated by insulating barrier, that is called a Josephson junction, and there is a current because of this tunneling of these Cooper pairs, and this current was experimentally, this is what Brian Josephson observed. I is equal to I naught sine delta, where delta is the superconducting phase between these two superconductors. And then all using this, and also this is the Josephson coupling energy, and all these things we discussed. And right, so all these things anyway I have discussed in my lecture classes. So let me then do one thing. Finally, this is the main thing that summarizes particular lecture 7. All these things are there that as you can see in these slides here. in this particular slide, week 7, and these are the stuffs that I have shown here. If you understand it, then you'll be able to understand the essence of the this is physics Nobel Prize also, and you can follow that famous 2004 paper that, and this particular figure also I have explained in the class that distinguishes between a transmon and a Cooper pair box, right? Cooper pair, in the case of the transmon, you see these oscillations are not there, but energeticity is not very good, but still you have a very clear energy levels are there. So transmon are pretty useful, and these are mostly used qubit at the moment. Okay, so finally, let me not, yeah, all these things I discussed. I have discussed in the problem solving session for the lecture 7, week 7. I discussed about all these things, dispersive coupling. That was not in the main lecture, but you please consider problem solving session as the main part of the course. Okay, don't think that those are some separate materials. It is intrinsically related to whatever I have covered in the lecture classes. So it's extremely important for you to go through the um, problem solving session as well. So all these things I discussed in the problem solving session. Okay, now lastly, regarding the textbook, this I already told you in my last live session. This covers parts before week 7 up to week 6. Most of the materials you are going to get in this quantum optics and this by Mark Fox and Introductory Quantum Optics by Gary and Knight. These are two classic textbooks. This Meister book and this Milborn and Wall's book is it may be very useful for you when you are dealing with week 6 and week 7. Okay. So I think that's what I wanted to speak. Now, if you have any query, you please let me know. Unfortunately, my camera is not working properly today somehow, so you may not be able to see you can hear my voice, but you'll not be able to see me. But that's all right. So you can ask me question now if you have any query. Just one thing I wanted to tell you that I try to teach as much things as possible, but please, don't get, terrified by seeing the volume of the things that I have taught you. As regard exam is concerned, exam is going to be very simple. If you have gone through the assignment problem properly, exam is going to be a cool affair because I'm not going to ask you derivation anything. Simple concepts. You just have to understand the essence of whatever is going on, and that's enough to qualify the exam. So exam is going to be an easy affair. That much I can say. Okay, so yeah, anything you want to ask me? If not, then maybe we can sign off, right? NPL team, we can end this session. So let me ask again, whoever is present, but I cannot see who is present, who is not. Let me ask once again, if you,
Sir,
whoever is present, participant, if you have any query, please tell me right now, because this is the last live
sir,
session for this course.
am I
Yes,
audible, sir?
yes.
Sir, is there
Yeah,
any
please go ahead.
platform to stim? Yes, sir. For example, is there any platform to stimulate this simulation part of the thing is available, sir? For example, I want
Yeah,
to simulate the equation.
yeah, it is there. Nowadays, there are many open source, this thing is there. Generally, I can tell about, because I am in this research area, particularly if you're talking about the last part, right? Optomechanics and superconducting circuits and so on. And even say quantum master equation, so on. Yes, you can simulate all these things. Python is particularly useful, and now there is a what is this called, quantum optics toolbox is there, quantum optics toolbox in Python, qtip, you may have heard about it, and I think I spoke about it in the last session also. You
Yes,
can
sir.
utilize qtip to simulate lots of the things. And even I
Okay, sir.
have heard maybe you can do that even in Qiskit also, particular Josephson junction and other parts. There are a lot of platforms nowadays, open
Okay,
software,
sir.
open platform, yeah.
Sir, in Percival, what is the quadratic phase, sir? Quadrature phase in
A
optics.
quadrature,
Yes.
right? That is
Yes.
that I talked about X and Y, right?
Yes, sir.
Yeah. So that I explained. You see, this X quadrature and Y quadrature. If you have gone through, my lectures there, then I explained that this, for example, this X quadrature is how it is defined. It is defined as A plus A dagger by 2, right?
Yes, sir.
Let me take you to that particular slide once again. Um, yeah. So also you see that the position for not this one, somewhere there I discussed. Mm, yeah, yeah, here, right? You see a plus a dagger by 2, that's the x quadrature, and y is equal to a minus a dagger. Now, physically speaking, this x quadrature is related to the position operator. If I talked about a normal quantum harmonic oscillator, correct?
Yes,
You
yes, sir.
see, that's how it is. This is represent x, and y quadrature is related to the momentum operator. Y quadrature is related to the momentum operator because that's how the momentum operator is defined, as you know. So physically speaking, that's what it means. And in the context of the light also, one is related to, you have, for example, another example, let me give you here. Uh, when we have discussed this in the context of Josephson junction, for example, here you see, here you can make it out that x quadrature is defined as a plus a dagger by 2. Now you just see this expression. If you just add this a plus a dagger, just if you see this, then you are going to get this in terms of the phi cap, which is the magnetic flux. So now here in the Josephson junction or superconducting qubit case, this magnetic flux quadrature is going to be associated with the x quadrature. Are you getting the idea?
Yes, sir.
A plus A dagger is associated with X quadrature, but here this X quadrature has a different meaning that refers to the magnetic flux operator, and the Y quadrature would be associated with the charge operator, would be associated with the charge, right? That's what it means. Am I clear?
Yes, sir.
Okay. Okay, then if there is no other query, and I thank all of you for attending it, and I once again urge all of you to please appear in the examination, and uh, these lectures will be available to you. Lecture notes are already there, so go through that, and I think you will learn a lot of things, and this would be pretty useful for you if you really want to do some advanced studies after this. So with this, let me thank all of you. Thanks a lot, and let me end the session now here. Okay,
Yes, sir.
Kolol, is
Thank you
it?
so much, sir.
Yeah. Okay, thank you.
Thank you, sir. Sir, can
Bye.
you guide us for any exam point of view related?
As I
Any
already I told
guidance?
you that for exam point of view, you just have to go through my uh, these assignments you do properly and problem solving session. That would be good
Yes, sir.
enough. and just stress on the concepts only. So I am just giving you the assignment as well as the problem solving session in such a way that if you just go through that, this exam will be very easy for you. Okay?
Yes, sir. Yes.
Okay. Okay
Thank
then.
you.
Bye. Yeah.